Welcome guys to today's class on the topic radioactivity. In today's class, we want to see what radioactivity is all about. What are the types of radioactivity? What are the possible causes or what can cause a particular element to disintegrate? Yes, so we have a lot to learn in today's class. Let's start with the definition of radioactivity. Radioactivity is defined as the spontaneous disintegration of radioactive elements, as the spontaneous disintegration of heavy nuclei with release of radiations. That means once a radioactive element, once an element which had the tendency to disintegrate, once it disintegrates, it releases radiations. The radiations it could release could be alpha particle, which we call helium atom or helium nuclei, or beta particle, gamma particle, and so on. Now, what are the possible types of radioactivity? 1. Natural radioactivity. When we talk about natural radioactivity, it means that that element has tendency to disintegrate on its own, and that is why it undergo natural radioactivity. So natural radioactivity is a type of radioactivity whereby an element which is a radioactive element disintegrates to its half naturally without anything inducing it to disintegrate, without anything causing it to disintegrate. That means when that radioactive element gets to its half-life, so to speak, it just disintegrates. Yes. And once this element disintegrates, it releases a lot of radiations. Yes. Some of these radiations it releases can be nuclear particles such as neutron. It could also release small nuclei such as helium particles or helium nuclei, which we call alpha particles. It can also release electromagnetic radiations such as gamma rays, X-rays, and so on. Look at what we mean. This is an example of radioactive element. We call this radium. This radium, once it disintegrates, look at the molar mass of it, 226. 226 is the molar mass, and 88 is the atomic mass. Okay? And so when this radium disintegrates, how will it disintegrate? Once it reaches its half-life, it will disintegrate naturally. The reason why this radium has tendency to disintegrate naturally is because the atomic number is greater than 83. Yes. And because it is one of the elements whose atomic number is greater than 83, it means that it can disintegrate naturally. It's unstable. So any element which has tendency to disintegrate to its half or to undergo radioactivity, it means that that element is unstable element. It must be an unstable element for it to disintegrate naturally. It must be an unstable element. And if you check the atomic number, most likely the atomic number should be greater than 83. Yes. So most of them are greater than 83. We will look into a lot of causes, but we are talking about some of the causes or some of the factors that can make a particular element to disintegrate. And we've said it must be unstable, and 2, the atomic number must be greater than 83. That is what will help it to disintegrate naturally. That means once it gets to its half-life, it disintegrates to half. Are you getting it? Now, this radium, once it disintegrates, is giving you what we call radon. Radon is Rn86, then 222. This is radon. This atomic number of radon, and this atomic number of radon. This is the molar this atomic number of radon. This mass number of radon. So once it disintegrates, it will be giving you helium particle. That means this plus this will give you this, this plus this will give you this. You get? So that is about natural radioactivity. That means it undergoes its disintegration naturally. There is nothing that will induce it to disintegrate. Okay? Then when we talk about artificial radioactivity, we call it transmutation. Artificial radioactivity is called transmutation. How does it occur? It occur when the nucleus of an element which may not have the tendency to disintegrate naturally, when the nucleus of it is bombarded with another element, or when it is bombarded by high energetic particle such as neutron. Once it's bombarded, it will lead to what? This disintegration. Okay, so in that one there must be what? Something or a particle that will do the induction, or that will induce that element to disintegrate. That's about artificial. It occurs artificially, meaning something must cause it to disintegrate, something must induce it to disintegrate. Okay, it is important to note that we have subatomic particles in this radioactivity. One is proton. This is called proton. Then the other one, this is for proton. Then we have what we call beta particle or electron. We write it this way. This is electron. This is some particles we can see in radioactivity. Then we also have what we call positron. This is called positron. Okay, we also have alpha particle. Alpha particle is this alpha particle. We also have gamma particle. That means the mass number is 0, atomic number is 0. This is gamma particle. Okay, so these are some of the subatomic particles we have in radioactivity. Okay, so it's important for you to note all these subatomic particles we just mentioned. Now we want to discuss radioactive decays. Radioactive decays we have. Yes, radioactive decays we have. One of it is electron emission. The second one is positron emission. The third one is alpha emission. The fourth one is electron capture. The fifth one is gamma emission. Okay, these are examples of radioactive decays we have. We want to look into them one after the other. Now, electron emission. When you talk about electron emission, the implication is that what you will be seeing is, and when lead at mass number 214, atomic number 82, disintegrate to bismuth to release electron. This electron or beta emission So that is how it occurs. When a radioactive particle decay to produce what? Bismuth with electron emission. We call it electron decay or electron emission. Then for positron emission, we say that when technetium, mass number 95, atomic number 43, disintegrate to form molybdenum plus positron being emitted, you call it positron emission. So whenever a radioactive element disintegrates to release positron, you call it positron what? Emission. For alpha emission, this is a typical example of alpha emission. When radium disintegrate to radon plus alpha particle, you call it what? Alpha emission. Then for electron capture, it means that an element just captured or pick an electron to disintegrate to another element, or to decay to another element, such as 4019 potassium. When it capture this electron, it will be producing argon 18 and 40. You now see that this capture this electron to be producing this. Yes, that's about what? Radioactivity. As this may not have the tendency to undergo radioactivity, but as it's bombarded by beta particles, it was able to produce another element, which is what? Argon. Then for gamma emission, when you come to gamma emission, it means that the radioactive element disintegrate to release what? Gamma. And how do it happen? What you do is, we give example. This is called thorium. This thorium disintegrate to release this element, electron, and what? Gamma. This is 234, 234, 234 plus this will give you 234. 90, this is 90, 91 minus this, 90 plus this, 90. That means it's producing what we call gamma particles or gamma ray. It's important for us to note that when this is an electron is bombarded with what? A positron. When an electron is bombarded to a positron, it produces a gamma what? Particle. That means it will vanish. When an electron is bombarded with a positron, it will what? Vanish, producing a gamma particle. So these are examples of radioactive decays we have. We also have nuclear fusion and nuclear fission as a way of dividing radioactivity. Nuclear fusion and nuclear fission. When we talk about nuclear fusion, it means that two elements or the two nucleus of an element joins together to form a what? A heavier what? Nuclei with release of radiation. Whereas nuclear fission means nucleus of a radioactive element disintegrates to produce its daughter elements with release of what? Radiation. That fission means breakdown, meaning the heavier nuclei breaks down to what? Its daughter particles with release of what? Radiations. Whereas fusion means joining together, meaning lighter particles or smaller particles of elements joins together to produce heavier elements with heavier nuclei. That is about nuclear fusion. And as this production is done, they release radiation as well. So that is about nuclear fusion and nuclear fission. Now for the one of calculation, it's important for you to know that if you are asked to calculate number of disintegration per second, yes, number of disintegration per second of a radioactive element is written this way. You say the formula is mass times decay constant times Avogadro's number all over molar mass. Okay, then if you are asked to calculate number of particle that half-life, if you are asked to calculate half-life of a radioactive element, because radioactivity obeys first order reaction law, what you do, since you obey first order reaction equation, what you do, half-life will be equals to 0.693 all over decay constant k, or 0.693 over lambda, depending on the symbol you want to use. Okay, that is about half-life. Then if you are asked to get amount of a radioactive element that remains after a particular time, tell them the amount is CT equals to the initial times 2.718 raised to power of minus what? K raised to power of minus KT. Okay, where K is the same thing with lambda, which is decay constant. Okay, that means this 2.71 is what we call E, exponential, or you say CT is equals to CO exponential minus KT, where CO is initial concentration or initial mass of that what? Particle. Then this is amount that remains. Then amount decayed is equals to CO minus CO bracket CO minus CT. CO initial minus the amount that what remains. You get the amount that decayed. Okay? And so once you have gotten this, if they ask you fraction that what remains, fraction remains, fraction remains, you say is equals to 1 over 2 raised to the power of T over half life. This is how to get the fraction that remains. Okay? This is how to get the fraction that remains. So fraction that decay, fraction decayed will be equal to 1 minus 1 over 2 raised to the power of T over what? Half. This is about fraction decay. These are some of the questions one can be asked in this topic. From here, once you have known your half-life equal to this over k, that means your k is equal to 0.693 over half-life. Okay? And so we have seen some things about this. Yes, some information about radioactivity. It's also important for us to note that it's also important for us to know that it's also important for us to know that if you have this is nitrogen plus alpha particle that it will be giving you proton plus yes, when you have this equation like this, that means this nitrogen is being bombarded with what? Helium nuclei or alpha particle to give you what? Proton and what? This, right? The implication is that you can package it this way. You say 14N7 bracket alpha particle and what? Proton 17. Okay. So this is another way of packaging this thing. That is the essence of writing this equation. If you want to see how to package this, look at it. So we have seen what radioactivity is all about. So when we talk about this half-life, we say this half-life is the time it will take a radioactive element to disintegrate to its what? Half. That means if this is a radioactive element, the time it will take for it to disintegrate to its half, then half will remain. When it gets to that time again, it will also, that one that remain will also disintegrate again to its half, half will remain. If you are asked to get it, you just say 0.693 over k. So these are possible information you can know with the time we have to talk about this. These are the possible information you need to know. That is the elementary aspect of radioactivity. You will see what to talk about radiopharmaceuticals in our channel. So this is few information I want to drop on radioactivity. You will also see questions, important questions you have to what? Know how to solve them. Thanks.